In 2007, a radio telescope in New Mexico picked up something impossible, a region of space so empty, so vast, that it challenged everything cosmologists thought they understood about the universe. The signal came from the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of space. But in one particular direction, toward the constellation Eridanus, the temperature readings dropped, not by much, just 70 millionths of a degree cooler than the surrounding sky. That tiny difference represented something enormous, a void in space stretching across more than 1 billion light-years, containing hundreds of thousands fewer galaxies than it should. Scientists call it the cold spot, or more formally, the Eridanus supervoid. According to the standard model of cosmology, structures this large shouldn't exist. The universe is only 13.8 billion years old, and there simply hasn't been enough time for gravity to carve out such a colossal emptiness. Yet the data keeps confirming it. This billion light-year hole in the cosmos is real. It's growing, and no one can fully explain why it's there. The discovery sent shockwaves through the physics community. Some researchers suggested it might be a statistical fluke, an artifact of measurement error. Others proposed exotic explanations, collisions with parallel universes, flaws in Einstein's theory of relativity, or evidence that our understanding of cosmic inflation is fundamentally incomplete. The more astronomers studied the cold spot, the stranger it became. Follow-up observations revealed not just one void but an entire complex of interconnected voids, each hundreds of millions of light-years across, stacked together like cosmic bubbles in the direction of Eridanus. What makes this discovery particularly unsettling is its implications. The cosmic microwave background is supposed to be almost perfectly uniform tiny ripples in temperature that represent the seeds from which galaxies, stars, and ultimately life emerged. These fluctuations are the fingerprints of quantum uncertainty from the first fraction of a second after the Big Bang, stretched across the entire sky by cosmic inflation. They're predictable, well understood, and follow precise statistical patterns, except in this one spot. The cold spot is 5 times larger and significantly colder than random chance would allow. It breaks the rules. The Eridanus supervoid sits roughly 3 billion light-years away, in a region of space between us and the cosmic microwave background. Light from the Big Bang's afterglow passes through this emptiness on its way to Earth, and as it does, something drains energy from the photons, cooling them ever so slightly. This effect, called the integrated Sachs-Wolf effect, occurs when light travels through expanding voids in an accelerating universe. But even accounting for this phenomenon, the cold spot remains far too cold, far too large, and far too empty. Some astronomers have searched for alternative causes. Could it be a measurement error? Extensive reanalysis using data from multiple satellites, WMAP, Planck, and others has confirmed the anomaly again and again. Could it be a foreground effect? Something between us and the cosmic microwave background that's blocking or altering the signal? Deep surveys of the region have found the supervoid itself, an underdense region containing significantly fewer galaxies than expected. But even the supervoid doesn't fully account for the temperature drop. Something else, something deeper, might be at work. The implications stretch beyond cosmology. If the cold spot represents a genuine departure from the standard model, it could be a window into new physics, dark energy behaving differently than expected, modifications to gravity on the largest scales, or evidence of cosmic events that occurred before or during inflation. It might even hint at the multiverse, the idea that our universe is just one bubble in an infinite foam of parallel realities. Some theoretical physicists have proposed that the cold spot could be a bruise left by a collision with another universe in the earliest moments of cosmic history, a scar on the fabric of space-time itself. For now, the Eridanus supervoid remains one of astronomy's greatest mysteries, an emptiness too large to ignore, a cold spot in the cosmic microwave background that refuses to be explained away. It sits there, a billion light-year question mark written across the sky, challenging scientists to rethink the universe's structure, its history, and perhaps even the laws that govern its existence. The discovery of the cold spot. The cosmic microwave background has been called the most important observation in cosmology. It's the radiation left over from the Big Bang, a faint glow that fills the entire universe and provides a snapshot of what the cosmos looked like just 380,000 years after its birth. At that early time, the universe had cooled enough for atoms to form, allowing light to travel freely through space for the first time. That primordial light has been traveling ever since, stretched and cooled by cosmic expansion into microwave wavelengths. Today, sensitive instruments can detect this radiation coming from every direction in the sky, revealing subtle variations in temperature that correspond to regions of slightly different density in the early universe. NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001 with the mission of mapping these temperature fluctuations across the entire sky with unprecedented precision. For years, WMAP collected data, measuring tiny temperature differences, typically just millionths of a degree, that trace the distribution of matter in the infant cosmos. Most of the sky showed exactly what cosmologists expected: a nearly uniform background peppered with small-scale fluctuations following well-understood statistical patterns. These patterns match predictions from cosmic inflation theory and fit neatly into the standard model of cosmology known as lambda CDM, which describes a universe dominated by dark energy and cold dark matter. But one region didn't fit. In 2005, a team of astronomers led by Lawrence Rudnick at the University of Minnesota noticed something unusual while analyzing WMAP data. Toward the constellation Eridanus, in the southern celestial hemisphere, there appeared a large patch of sky where the cosmic microwave background was measurably colder than its surroundings, not by a huge amount, but by roughly 70 microkelvin, or 70 millionths of a degree Celsius. The anomaly spanned an enormous angular scale, covering about 5 to 10 degrees across the sky. That might not sound like much, but at cosmological distances, it translates to a physical structure more than 1 billion light-years in diameter. The team spent months verifying their findings, ruling out instrumental errors and foreground contamination from sources within our own galaxy. Radio surveys, infrared observations, and optical telescopes all confirmed that the region appeared genuinely underdense in galaxies compared to the cosmic average. Something about this particular patch of space was different, and the cold spot, as it came to be known, became one of the most scrutinized features in the entire cosmic microwave background. Follow-up studies intensified after the European Space Agency's Planck satellite began operations in 2009. Planck carried even more sensitive instruments than WMAP, capable of measuring temperature variations with extraordinary precision. When Planck's data became available in 2013, astronomers immediately turned their attention to the cold spot. The results confirmed WMAP's findings. The anomaly was real, persistent, and unexplained. Planck's measurements showed that the cold spot wasn't just a single cold region but appeared to have internal structure, a complex pattern of cooler and warmer patches within the larger anomaly, suggesting it might be caused by multiple overlapping voids or some other intricate cosmic architecture. The discovery posed a fundamental problem. According to the standard model of cosmology, temperature fluctuations in the cosmic microwave background should follow a specific statistical distribution determined by the physics of the early universe. These fluctuations arise from quantum uncertainty during cosmic inflation, blown up to cosmic scales and frozen into the fabric of space. Over billions of years, gravity amplified these initial ripples, turning slightly denser regions into galaxies and galaxy clusters, while leaving slightly less dense regions as voids. But the process has limits. The universe is only 13.8 billion years old, and gravity works at a finite speed. There hasn't been enough time for structures larger than a few 100 million light-years to form through normal gravitational collapse. Yet the cold spot appeared to correspond to a structure or a lack of structure stretching across more than 1 billion light-years. If it truly represented a supervoid, an enormous underdense region of space, it would be one of the largest known structures in the observable universe. But how could such a vast emptiness have formed in the time available? And more perplexing still, why would it produce such a pronounced cold spot in the cosmic microwave background? These questions drove astronomers to conduct extensive galaxy surveys of the Eridanus region. Using ground-based telescopes and space observatories, they mapped the distribution of galaxies in 3 dimensions, measuring their distances through redshift, the stretching of light caused by cosmic expansion. The surveys revealed something striking. The cold spot did indeed coincide with an underdense region, a supervoid containing significantly fewer galaxies than expected. Later studies identified not just one void but a series of interconnected voids, forming what some researchers called a supervoid complex, stretching across 3 billion light-years of space. The existence of the supervoid provided a partial explanation for the cold spot through a phenomenon called the integrated Sachs-Wolf effect. When photons from the cosmic microwave background travel through an expanding void in an accelerating universe, they lose energy, becoming slightly cooler. This effect occurs because dark energy causes space to expand faster over time, meaning that voids grow as light passes through them. Photons climbing out of a void's gravitational potential lose more energy than they gain falling in, resulting in a net cooling. Simulations showed that a supervoid the size of the one in Eridanus could produce some cooling, perhaps accounting for part of the cold spot's temperature deficit. But only part. Even with the integrated Sachs-Wolf effect, the supervoid couldn't fully explain the magnitude of the cold spot. The temperature drop remained too large, too cold by roughly 30 to 50% compared to theoretical predictions. This meant either the supervoid was even more extreme than measurements suggested, or something not accounted for in standard cosmology was contributing to the anomaly. Mainstream cosmologists remained cautious. While the cold spot was certainly unusual, they argued, it wasn't necessarily a sign of new physics. The universe is vast, and rare events do occur. Moreover, accurately calculating the statistical significance of the cold spot proved surprisingly difficult. Different methods of analysing the data yielded different probabilities, ranging from moderately unlikely to extremely improbable. Some analyses suggested the anomaly was less than 3 standard deviations from the mean, notable but not conclusive evidence of a breakdown in cosmological theory. The cosmic microwave background. To understand why the cold spot matters, you have to understand the cosmic microwave background itself, what it is, where it comes from, and why cosmologists consider it the single most important source of information about the early universe. The cosmic microwave background is ancient light, the oldest light we can observe. It comes from a specific moment in cosmic history called recombination, which occurred roughly 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time. Before recombination, the universe was a hot, dense plasma, a roiling sea of charged particles where photons constantly scattered off free electrons. In this opaque state, light couldn't travel far without being absorbed or deflected. The universe was effectively a cosmic fog, impenetrable to any observer trying to see through it. But as expansion continued, temperatures dropped. When the universe cooled below about 3000 Kelvin, electrons began binding to protons, forming stable hydrogen atoms. This process, called recombination, removed most of the free electrons from the cosmic plasma. Without free electrons to scatter off, photons could suddenly travel through space unimpeded. The universe became transparent, and light streamed freely in all directions. That moment of transparency marked a turning point. The photons released during recombination have been traveling through space ever since, forming what we now observe as the cosmic microwave background. Originally, these photons had wavelengths corresponding to visible and infrared light, but 8 billion years of cosmic expansion have stretched them into microwave wavelengths, cooling them from thousands of degrees to just 2.7 Kelvin above absolute zero. Today, this faint glow fills the entire universe, arriving at Earth from every direction in the sky. It's the afterglow of creation, a snapshot of the universe at 380,000 years old, preserved and stretched across cosmic time. What makes the cosmic microwave background so valuable to cosmologists is its near-perfect uniformity. No matter which direction you look, the temperature is almost exactly the same, 2.7 Kelvin, give or take tiny fractions of a degree. This uniformity tells us that the early universe was remarkably smooth and homogeneous, with matter and energy distributed almost evenly across space. But almost is the key word. Within that uniformity lie subtle variations, temperature fluctuations typically measuring only tens of microkelvin millionths of a degree. These tiny ripples are the seeds of all cosmic structure. Regions that were slightly denser than average eventually collapsed under gravity to form galaxies, stars, and planets. Regions that were slightly less dense became the voids between galaxy clusters. The pattern of these fluctuations is not random. It contains information about the fundamental properties of the universe, its age, composition, geometry, and initial conditions. By analysing the size, distribution, and statistical properties of the temperature variations, cosmologists can determine how much ordinary matter, and dark energy the universe contains. They can measure the rate of cosmic expansion and test theories about the universe's earliest moments. The cosmic microwave background is effectively a cosmic fossil, preserving the imprint of physical processes that occurred when the universe was a tiny fraction of its current age. The breakthrough came with WMAP in 2001 and later with Planck in 2009. These space-based observatories mapped the cosmic microwave background across the entire sky with extraordinary sensitivity and angular resolution, measuring temperature variations as small as a few microkelvin across angular scales ranging from the size of the full moon down to fractions of a degree. The resulting maps revealed a complex pattern of hot and cold spots, a cosmic web of temperature fluctuations that cosmologists could analyze statistically to extract information about the universe's properties. When analyzed through the lens of the lambda CDM model, the cosmic microwave background fits predictions with stunning accuracy. The model describes a universe that began with a rapid period of exponential expansion called inflation, followed by a long era dominated by matter, and finally transitioning to an era dominated by dark energy. Dark matter, which interacts only through gravity, makes up about 27% of the universe's total energy density. Ordinary matter, atoms, stars, planets accounts for just 5%. The remaining 68% consists of dark energy, a mysterious force causing the universe's expansion to accelerate. This model successfully predicts the statistical properties of temperature fluctuations in the cosmic microwave background. It explains why certain angular scales show stronger fluctuations while others show weaker ones. It accounts for the positions and heights of the so-called acoustic peaks in the power spectrum, features that arise from sound waves propagating through the primordial plasma before recombination. Every measurement WMAP and Planck made confirmed the lambda CDM model's predictions to remarkable precision, cementing it as the standard model of cosmology. But the cold spot doesn't fit. Its size, temperature deficit, and statistical properties fall outside the range of fluctuations the standard model predicts. According to lambda CDM, temperature variations in the cosmic microwave background should follow a Gaussian distribution, a bell curve, where most fluctuations cluster around the average and extreme deviations become exponentially rarer. The cold spot represents a significant outlier, several standard deviations from the mean depending on how you calculate it. While not impossible under standard cosmology, it's improbable enough to raise questions. Some researchers have argued that we're simply seeing a rare but expected statistical fluctuation. If you survey enough of the sky, you're bound to find a few unusual features just by chance. Others contend that the cold spot, combined with other anomalies in the cosmic microwave background, points to something deeper, perhaps a limitation in the lambda CDM model, or evidence of processes that occurred during or before inflation that the standard model doesn't account for. The cosmic microwave background also contains information encoded on different angular scales. Large-scale features, spanning many degrees across the sky, correspond to physical structures and processes on enormous cosmic scales. These large-scale fluctuations are particularly sensitive to events that occurred very early in the universe's history, during the inflationary epoch when quantum fluctuations were stretched to macroscopic sizes. Smaller-scale features, on the other hand, reflect processes that happened later, closer to recombination, when acoustic oscillations, sound waves in the primordial plasma, left their imprint on the distribution of matter. The cold spot is a large-scale feature. It spans roughly 5 to 10 degrees across the sky, corresponding to physical scales exceeding 1 billion light-years. Features this large probe the universe's structure on its grandest scales and tests the limits of what gravitational collapse and cosmic expansion can create in the time available. If the cold spot truly represents a single coherent structure or a series of causally connected voids, it challenges the assumption that the universe is statistically homogeneous and isotropic on the largest scales, one of the foundational principles of modern cosmology. Statistical anomalies and the probability problem. When the cold spot first appeared in WMAP data, astronomers faced a critical question. Was it a genuine cosmological anomaly, or simply a statistical fluke, an inevitable outlier in a large dataset? After all, if you measure enough points across the sky, probability dictates that some will deviate significantly from the average purely by chance. The challenge lay in determining how unusual the cold spot really was, and whether its existence warranted revising our understanding of the universe. Statistical analysis of the cosmic microwave background begins with the assumption that temperature fluctuations follow a Gaussian random field, a mathematical model where variations arise from random processes with no preferred locations or directions. In this framework, the probability of finding a temperature fluctuation of a given size and amplitude can be calculated based on the statistical properties of the field as a whole. The cosmic microwave background, shaped by quantum fluctuations during inflation and subsequent gravitational evolution, should produce fluctuations that fit this model almost perfectly. The cold spot doesn't. Its temperature deficit of roughly 70 microkelvin, combined with its enormous angular size, places it at the tail end of the probability distribution rare, but perhaps not impossibly so. Early estimates suggested the probability of such a feature arising by chance was somewhere between 1 inch 50 and 1 inch 100, depending on the specific statistical test applied. That's uncommon, but not unprecedented. In a sky containing millions of resolution elements, finding one or two unusual features isn't shocking, but other analyses painted a more troubling picture. When astronomers examined the cold spot in the context of the entire cosmic microwave background, considering not just its individual properties but also its relationship to surrounding features, the statistics became harder to dismiss. The cold spot sits within a broader region of lower than average temperature, extending across tens of degrees of sky. This larger cold patch contains multiple smaller cold spots, of which the Eridanus feature is the most pronounced. The probability of finding such a cluster of cold anomalies in close proximity, all aligned in the same general direction, dropped significantly, perhaps to less than 1 inch 100 or even 1 inch 200 inches some models. The existence of multiple anomalies complicates probability calculations because it introduces a look elsewhere effect. If you search a dataset for anomalies without specifying in advance what you're looking for, you increase the chances of finding something unusual purely by chance. In other words, if you examine enough different features using enough different statistical tests, you're almost guaranteed to find a few that appear anomalous. This doesn't mean the anomalies are meaningless, but it does mean their statistical significance must be adjusted to account for the fact that they were discovered through exploratory analysis rather than predicted beforehand. A 2015 study attempted to address this by running thousands of simulations of the cosmic microwave background based on the Lambda CDM model and searching each one for cold spot-like features using the same detection. Algorithms applied to real data. The researchers found that roughly 2 to 3% of simulations produced anomalies comparable to, or more extreme, than the observed cold spot. This suggested that while the feature was unusual, it wasn't beyond the realm of possibility within standard cosmology. The study concluded that the cold spot could plausibly be a rare statistical fluctuation rather than evidence of new physics. But not everyone agreed with that interpretation. Critics pointed out that the simulations only tested whether a cold spot-sized anomaly could arise by chance. They didn't test whether it would arise in the same location as other anomalies, or whether it would exhibit the same internal structure seen in observations. When researchers looked more closely at the cold spot's internal morphology, the pattern of warmer and cooler patches within the larger cold region, they found additional unexpected features. The cold spot appeared to have a cold core, surrounded by a slightly warmer ring, a structure that didn't match the predictions of standard Gaussian random fields. Another complication arose from attempts to identify a physical cause for the cold spot. If it was purely a primordial fluctuation imprinted during inflation, then its temperature deficit should reflect only the density contrast present in the early universe. But if it was also influenced by intervening structures such as a supervoid along the line of sight, then its temperature deficit could be amplified through the integrated Sachs-Wolf effect. This raised the question, how much of the cold spot's temperature deficit comes from primordial fluctuations, and how much comes from the supervoid? Galaxy surveys of the Eridanus region provided some answers. In 2015, a team led by Istvan Sapudi at the University of Hawaii published a study identifying a large, underdense region, or supervoid, aligned with the cold spot. The supervoid spanned roughly 1.8 billion light-years and contained about 10,000 fewer galaxies than a typical region of that size. The researchers calculated that this supervoid, through the integrated Sachs-Wolf effect, could produce a temperature deficit of roughly 10 to 20 microkelvin, enough to partially explain the cold spot, but not nearly enough to account for the full 70 microkelvin deficit. This finding was both reassuring and troubling. On one hand, it confirmed that a physical structure existed in the direction of the cold spot, providing a partial explanation for the anomaly. On the other hand, it meant that something else, either an even larger supervoid, an unusually strong primordial fluctuation, or some unaccounted for physical process was needed to explain the remaining temperature deficit. The supervoid alone wasn't sufficient. The debate over the cold spot's statistical significance continues. Some researchers maintain that it represents a genuine anomaly, a feature unlikely to arise by chance and potentially pointing toward new physics or limitations in the standard cosmological model. Others argue that it's a rare but expected statistical fluctuation, the cosmic equivalent of flipping a coin 20 times and getting 15 heads unusual, but not impossible. The truth probably lies somewhere in between. The cold spot is more unusual than a typical fluctuation, but not so extreme as to definitively rule out chance. The integrated Sachs-Wolf effect. One of the most important clues to understanding the cold spot comes from a subtle phenomenon in cosmology known as the integrated Sachs-Wolf effect. This effect describes how photons from the cosmic microwave background gain or lose energy as they pass through gravitational fields that change over time. In a static universe where gravitational potentials remain constant, photons climbing out of a gravitational well lose exactly as much energy as they gained falling in, resulting in no net change. But in an evolving universe, where structures grow or decay over time due to cosmic expansion and dark energy, this symmetry breaks down. The integrated Sachs-Wolf effect becomes significant in two scenarios. The first occurs during the early universe when matter dominated the cosmic energy budget and structures were rapidly forming. As photons from the cosmic microwave background passed through collapsing regions that would eventually become galaxy clusters, the deepening gravitational wells caused photons to gain energy, producing small hotspots in the microwave sky. The second scenario, and the one relevant to the cold spot, occurs in the late universe when dark energy dominates. In this regime, cosmic expansion accelerates, causing large-scale structures like voids to expand faster than they would in a matter-dominated universe. Here's how it works. Imagine a photon from the cosmic microwave background traveling through a vast, underdense region, a void containing fewer galaxies and less matter than average. As the photon enters the void, it climbs out of the gravitational potential well surrounding the denser regions outside the void, losing energy in the process. It then travels through the void's interior, where gravitational forces are weaker, before eventually climbing back into the gravitational field of the denser regions on the far side. If the universe were static or expanding at a constant rate, the energy the photon loses entering the void would exactly cancel the energy it gains exiting, resulting in no net change. But in an accelerating universe driven by dark energy, the void itself expands while the photon is crossing it. By the time the photon exits the void, the gravitational potential well on the far side has become shallower than the one the photon climbed out of on the entrance side. As a result, the photon gains less energy exiting than it lost entering. The net effect is that the photon emerges from the void with less energy, and therefore longer wavelength and lower temperature than it had before encountering the void. Multiply this effect across billions of photons passing through billions of voids across cosmic time, and you get a subtle imprint on the cosmic microwave background. Voids appear as cold spots. Theoretical calculations based on the standard lambda CDM cosmology predict that typical voids, ranging from a few 100 million to perhaps 500 million light-years across, should produce temperature deficits in the cosmic microwave background of roughly 5 to 15 microkelvin. Observations confirm this. By cross-correlating maps of the cosmic microwave background with three-dimensional galaxy surveys that identify the locations of voids, astronomers have detected the integrated Sachs-Wolf effect as a statistical signal. On average, the direction of known voids corresponds to slightly colder regions of the microwave background, exactly as predicted. But the cold spot presents a problem. Its temperature deficit of 70 microkelvin is far larger than what typical voids should produce. Even an exceptionally large void, one spanning 1 billion light-years or more, would struggle to generate such a strong cooling signal through the integrated Sachs-Wolf effect alone. Simulations suggest that a void of that size might produce a temperature drop of 20 to 30 microkelvin at most. That's significant, but it accounts for less than half of the observed deficit. This discrepancy led researchers to search for extraordinarily large voids in the direction of the cold spot. If one existed, it might provide the missing piece of the puzzle. In 2015, Istvan Sapudi and his colleagues published results from an analysis combining data from multiple galaxy surveys, including the WISE satellite's infrared observations and the Pan-STARRS optical survey. They identified a region of significantly reduced galaxy density aligned with the cold spot, stretching across roughly 1.8 billion light-years at a distance of about 3 billion light-years from Earth. This supervoid, they argued, was one of the largest known underdense regions in the observable universe. The team calculated that a void of this size, given its depth and distance, could produce a temperature deficit of approximately 9 to 20 microkelvin through the integrated Sachs-Wolf effect. That's substantially less than the cold spot's 70 microkelvin deficit, but it provides a partial explanation. The remaining temperature deficit would have to come from primordial fluctuations, the random density variations present in the early universe that seeded all cosmic structure. In other words, the cold spot might result from a combination of two effects: an unusually strong primordial cold spot amplified by the presence of an unusually large supervoid along the same line of sight. However, not everyone accepts this explanation. Critics point out several issues. First, the magnitude of the supervoid's contribution to the cold spot depends sensitively on its exact size, density contrast, and distance, all of which remain uncertain. Different galaxy surveys yield somewhat different measurements, and systematic errors in determining galaxy redshifts can significantly affect estimates of the void's properties. If the void is smaller or shallower than initially reported, its contribution to the cold spot shrinks even further. Third, even if the supervoid explains part of the cold spot, the remaining primordial contribution would still be statistically unusual. A 50 microkelvin primordial cold spot is rarer than a 70 microkelvin one, but not by much. It still sits at the tail of the probability distribution predicted by standard inflation models. So while invoking the integrated Sachs-Wolf effect helps, it doesn't fully resolve the statistical tension. Despite these uncertainties, the integrated Sachs-Wolf effect remains the leading explanation for at least part of the cold spot's temperature deficit. It provides a physical mechanism connecting the observed microwave background anomaly to large-scale structure in the universe, grounding the phenomenon in well-understood physics rather than requiring exotic new theories. If correct, the cold spot serves as a remarkable example of how gravitational effects in an accelerating universe can leave detectable imprints on the cosmic microwave background, turning voids, the emptiest regions of space, into visible features in the sky's oldest light. Mapping the supervoid. Once astronomers hypothesized that a supervoid might explain the cold spot, the next challenge was to map it to measure its size, depth, and three-dimensional structure with enough precision to test whether it could account for the observed temperature deficit. This proved far more difficult than it might sound. Unlike dense clusters of galaxies, which blaze with light and X-ray emission, voids are defined by what's absent. They're regions with significantly fewer galaxies than average, making them difficult to detect and even harder to characterize accurately. The basic technique involves galaxy redshift surveys. Astronomers observe thousands or millions of galaxies across a region of sky, measuring the spectrum of light from each one. Because cosmic expansion stretches the wavelengths of light traveling through space, galaxies farther away appear redder. Their spectral lines shift toward longer wavelengths. By measuring this redshift, astronomers can estimate a galaxy's distance and place it within a three-dimensional map of the universe. When enough galaxies are mapped, patterns emerge: clusters where galaxies crowd together, filaments connecting clusters, and voids where galaxies are sparse. Identifying a void requires statistical comparison. Astronomers divide space into cells or regions and count how many galaxies occupy each one. If a region contains significantly fewer galaxies than the cosmic average, it qualifies as underdense a void, but significantly fewer is subjective. How much below average must the galaxy count be? And how large must the region be to constitute a void rather than just a random underdense patch? Different studies use different thresholds, leading to different void catalogues and some confusion when comparing results. For the cold spot, the challenge was compounded by its location. At a distance of roughly 3 billion light-years, the Eridanus region sits at the edge of where detailed galaxy surveys have good coverage. Obtaining redshifts for faint, distant galaxies requires significant telescope time, and even then, many galaxies are too faint to observe spectroscopically. The Eridanus region sits at the edge of where detailed galaxy surveys have good coverage. Obtaining redshifts for faint, distant galaxies requires significant telescope time, and even then, many galaxies are too faint to observe spectroscopically. Astronomers often resort to photometric redshifts distance estimates based on galaxies' colours and brightness rather than detailed spectra. These photometric redshifts are less accurate, introducing uncertainties that can blur the boundaries of voids and make their properties harder to pin down. The 2015 study by István Sapudi and colleagues used data from multiple surveys to construct a three-dimensional map of galaxy density in the direction of the cold spot. They combined the WISE infrared survey, which catalogued millions of galaxies across the sky, with the Pan-STARRS optical survey, which provided photometric redshifts. By analysing the density of galaxies as a function of distance and position, they identified a region centred roughly 3 billion light-years away, where galaxy density dropped significantly by about 20 to 30% below the cosmic average. This underdensity extended over an enormous volume, spanning approximately 1.8 billion light-years across. That made it one of the largest voids ever detected. The team dubbed it the Eridanus Supervoid and calculated that it contained roughly 10,000 fewer galaxies than a typical region of the same size. They argued that a structure this large and this underdense could produce a temperature deficit in the cosmic microwave background through the integrated Sachs-Wolf effect, contributing to the cold spot. But follow-up studies using different datasets yielded mixed results. A 2017 analysis using the Sloan Digital Sky Survey and other spectroscopic catalogues found evidence for underdensity in the Eridanus region, but suggested the effect was weaker and more diffuse than Sapudi's team reported. Instead of a single giant void, the data hinted at a series of smaller voids stacked along the line of sight, creating a void complex rather than one coherent structure. The distinction matters because multiple smaller voids would produce a smaller cumulative, integrated Sachs-Wolf effect than a single giant void of equivalent total volume. Another complication arose from the fact that voids aren't empty. They contain some galaxies just fewer than average. The exact galaxy deficit within a void affects its gravitational potential, and therefore the strength of the integrated Sachs-Wolf effect it produces. A void with 20% fewer galaxies has a shallower gravitational potential than one with 40% fewer, and thus produces less cooling. Measuring this deficit accurately requires comprehensive galaxy surveys that don't miss faint galaxies or suffer from selection biases. In practice, achieving this is difficult, especially at large distances where only the brightest galaxies are easily observable. Radio surveys offered an alternative approach. Neutral hydrogen gas emits radiation at a wavelength of 21 centimeters, and large radio telescopes can detect this signal from galaxies billions of light-years away. By mapping the distribution of hydrogen, astronomers can trace the distribution of matter even in regions where optical galaxy surveys struggle. However, detecting faint hydrogen signals requires extremely sensitive instruments and long observation times, and the Eridanus region has not yet been comprehensively mapped in 1 centimeter emission. Gravitational lensing provided yet another tool. When light from distant galaxies passes through a foreground structure like a void, the gravitational field of the intervening matter slightly bends the light, distorting the shapes of background galaxies. In principle, by measuring these distortions statistically across many galaxies, astronomers can map the distribution of mass along the line of sight, revealing voids as regions where lensing is weaker than average. In practice, the signal is subtle, and detecting it requires large datasets with precise shape measurements. Some studies have attempted to use lensing to map the Eridanus region, with tentative evidence supporting the presence of a large underdense structure, but the results remain inconclusive. The most detailed three-dimensional map to date comes from combining multiple surveys and techniques. Researchers have cross-referenced optical data from Sloan, infrared data from WISE, spectroscopic redshifts from large telescope campaigns, and even X-ray observations of galaxy clusters to build a composite picture of the Eridanus region's structure. This map reveals a complex filamentary cosmic web punctuated by voids of various sizes. The largest underdense region aligns with the cold spot, but it's not a simple spherical void. Instead, it appears elongated and irregular, with tendrils of galaxies threading through it and connecting to surrounding clusters. One intriguing possibility is that the Eridanus supervoid is part of a much larger pattern, a void supercluster, or a series of interconnected voids, forming a particularly empty patch of the cosmic web. Simulations of large-scale structure formation show that voids naturally organize into networks, merging and growing as the universe expands. In regions where several large voids happen to align, the cumulative effect could create an exceptionally underdense volume, more extreme than any single void. If the cold spot sits within such a region, it might represent a rare but statistically plausible outlier, a cosmic accident of geometry rather than a breakdown of physics, cosmic inflation and large-scale structure. To understand why the Eridanus supervoid poses such a challenge to cosmology, we need to revisit cosmic inflation, the theory describing the first fraction of a second after the Big Bang. Inflation proposes that the universe underwent a brief but explosive period of exponential expansion, growing from subatomic scales to macroscopic dimensions in less than a trillionth of a second. This rapid expansion smoothed out any initial irregularities, leaving the universe remarkably uniform. But quantum fluctuations, random jitters inherent in the fabric of space-time, were also stretched to cosmic scales, seeding the density variations that eventually grew into galaxies, clusters, and voids. Inflation makes specific predictions about the properties of these primordial fluctuations. They should be nearly scale invariant, meaning that fluctuations of different sizes have roughly similar amplitudes. They should also be Gaussian, following a bell curve distribution with no preferred locations or directions. And they should be adiabatic, meaning that fluctuations in matter density are accompanied by corresponding fluctuations in radiation density. These properties have been tested extensively through observations of the cosmic microwave background, and the data match the predictions with extraordinary precision. However, inflation also imposes limits on the size of structures that can form. Because the universe is finite in age, there's only been so much time for gravity to amplify primordial fluctuations into large-scale structures. The fastest structures can grow is set by the speed of light and the rate of cosmic expansion. Roughly speaking, the largest structures that could have formed through gravitational collapse since the Big Bang are a few 100 million light-years across. Anything significantly larger shouldn't exist, it would require more time than the universe has been around. The Eridanus supervoid, stretching across more than 1 billion light-years, pushes against this limit. If it's truly a single coherent structure, formed through gravitational evolution, it's one of the largest ever discovered. Other contenders include the Sloan Great Wall, a filamentary structure stretching 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. These structures, like the supervoid, challenge our understanding of how quickly cosmic structure can assemble. One possible resolution is that these structures aren't truly coherent in a physical sense. The Sloan Great Wall, for example, isn't a single-bound object but rather a statistical overdensity, a region where galaxy clusters happen to align along a common axis across vast distances. Similarly, the Eridanus supervoid might not be a single void but a series of smaller voids that happen to align in our line of sight, creating the appearance of a much larger structure. If true, this would ease the tension with inflation, since each individual component would be within the expected size range. But proving whether the supervoid is one structure or many requires detailed three-dimensional mapping, and as we've seen, that's difficult to achieve at cosmological distances. The galaxy surveys available so far don't have sufficient resolution to definitively distinguish between a single giant void and a series of aligned smaller ones. Future surveys with better depth and coverage may resolve the issue, but for now, the question remains open. Another complication arises from the way inflation sets the initial conditions for structure formation. Inflation predicts that primordial fluctuations should follow a specific statistical distribution, characterized by a quantity called the power spectrum. This spectrum describes how much fluctuation power exists at different scales. Large-scale fluctuations corresponding to superclusters and voids, small-scale fluctuations corresponding to galaxies and clusters. Observations of the cosmic microwave background have measured this power spectrum with high precision, and it matches inflation's predictions almost perfectly. But there's a catch. The power spectrum describes averages, not individual features. It tells us, on average, how much fluctuation we should expect at a given scale, but it doesn't predict where specific structures will appear. In any given realization of the universe, rare outliers will exist, regions where fluctuations happen to be stronger or weaker than average. The question is whether the cold spot and its associated supervoid represent a normal outlier within the predicted distribution or something more extreme. Statistical analyses suggest the supervoid is unusual but not impossible. Simulations of large-scale structure formation, based on the lambda CDM model, occasionally produce voids approaching the size of the Eridanus supervoid. They're rare, appearing in perhaps 1 to 2% of simulated universes, but not so rare as to require abandoning the standard model. Combined with a primordial cold spot in the cosmic microwave background, which could also occur in about 1 to 2% of realizations, the overall probability of observing something like what we see in Eridanus drops to perhaps 1 inch 1,000 or 1 inch 5,000. That's low, but given the vast number of resolution elements across the entire sky, it's not beyond the realm of chance. Some cosmologists argue that we're simply seeing the universe's natural statistical variability. Just as flipping a coin 100 times will occasionally yield 60 heads or 40 tails, surveying billions of cubic light years will occasionally reveal unusually large voids or unusually strong temperature fluctuations. The cold spot, in this view, is cosmology's equivalent of a 6-0, head sequence rare and noteworthy, but not miraculous. Others are less sanguine. They point out that the cold spot is just one of several anomalies in the cosmic microwave background. The hemispherical asymmetry, the low quadrupole power, and the so-called axis of evil all hint that something might be missing from the standard inflation picture. Perhaps inflation didn't completely erase all traces of what came before. Perhaps there are preferred directions or locations in the universe, violating the assumption of isotropy. Or perhaps the inflaton field, the hypothetical field driving inflation, had properties slightly different from the simplest models, leading to a non-Gaussian distribution of fluctuations with a higher probability of rare events. Testing these ideas requires more data. Future cosmic microwave background experiments, such as the Simons Observatory and CMB S4, will map the microwave sky with even greater sensitivity and resolution than Planck, potentially revealing additional anomalies or confirming that the cold spot is an isolated outlier. Meanwhile, next-generation galaxy surveys like Euclid and the Vera Rubin Observatory's Legacy Survey of Space and Time will map the three-dimensional distribution of galaxies across billions of light-years, providing a much clearer picture of the cosmic web's structure and whether supervoids as large as the Eridanus feature are common or exceptional. Alternative explanations and exotic theories. While the combination of a primordial fluctuation and a supervoid-induced integrated Sachs-Wolf effect remains the mainstream explanation for the cold spot, it hasn't satisfied everyone. The statistical tension, combined with other anomalies in the cosmic microwave background, has prompted some physicists to explore alternative explanations ideas that push beyond the standard cosmological model and venture into speculative territory. One of the most intriguing proposals suggests the cold spot might be a relic of cosmic inflation itself, but not in the way standard models predict. In the simplest inflation scenarios, a single scalar field called the inflaton drives the exponential expansion, and quantum fluctuations in this field seed all primordial density variations. But more complex models allow for multiple fields or non-standard dynamics that could produce unusual signatures in the cosmic microwave background. For example, if the inflaton field experienced a brief deviation from its smooth rolldown, perhaps due to a feature in its potential energy curve, it might have generated an unusually strong fluctuation at a specific scale, creating a localized cold spot larger than random chance would predict. Another possibility involves the geometry of space itself. Standard cosmology assumes the universe is spatially flat, meaning parallel lines never converge or diverge, and the angles of a triangle always sum to 180 degrees. Observations of the cosmic microwave background support this assumption. To high precision, the universe appears flat to within a fraction of a percent, but small deviations from perfect flatness are allowed, and some models suggest these could produce large-scale anomalies. If the universe has slight positive curvature, like the surface of a sphere, or negative curvature, like a saddle, the way temperature fluctuations propagate through space would change subtly, potentially producing features like the cold spot. More exotic still is the multiverse hypothesis. In eternal inflation models, our observable universe is just one bubble in an infinite foam of universes, each with potentially different physical laws and initial conditions. These bubbles form when different regions of space stop inflating at different times, creating separate pocket universes. If two such bubbles collided during or shortly after inflation, the collision could leave a distinctive imprint on the cosmic microwave background, a disc-shaped region of reduced or enhanced temperature, possibly matching the cold spot's profile. This idea, first proposed in the late 2000s, generated significant excitement because it offered a testable prediction of multiverse theories, which are often criticized as unfalsifiable. If the cold spot were truly a collision signature, it should have specific geometric properties, a nearly circular boundary, a characteristic temperature profile, and possibly even ripples or secondary features around the edges. Researchers analyzed the cold spot's shape and temperature distribution, searching for these signatures. The results were inconclusive. COS. While the cold spot is roughly circular, its exact shape and internal structure don't perfectly match the predictions of bubble collision models. Most cosmologists now consider a bubble collision unlikely, though the idea hasn't been definitively ruled out. Another speculative explanation invokes topological defects, exotic structures that could have formed during phase transitions in the early universe. Just as water crystallizing into ice can form cracks and boundaries, the cooling universe might have produced defects in the fabric of spacetime itself, cosmic strings, domain walls, or monopoles. These defects, if they existed and passed through the region of space that would later become the cold spot, could have left gravitational imprints that seeded an unusually large void. However, most topological defect models predict much smaller structures, and there's no direct evidence such defects exist in our universe. Some researchers have even questioned whether dark energy, the mysterious force driving cosmic acceleration, might behave differently in different regions of space. If dark energy's density or equation of state varies slightly from place to place, it could cause voids to expand at different rates, potentially producing unusually large underdense regions and stronger than expected integrated Sachs-Wolf effects. This idea, sometimes called inhomogeneous dark energy, remains speculative and lacks observational support, but it illustrates the lengths to which scientists will go to explain the cold spot if standard models fall short. A related proposal suggests modifications to general relativity on cosmological scales. Einstein's theory has been tested extensively within our solar system and in extreme environments like neutron stars and black holes, but its validity on scales of billions of light-years is less certain. Some modified gravity theories, designed to explain cosmic acceleration without invoking dark energy, predict that gravitational potentials should decay more rapidly on large scales, enhancing the integrated Sachs-Wolf effect. If true, a void of the Eridanus supervoid size could produce a stronger temperature deficit than standard relativity predicts, potentially accounting for the full magnitude of the cold spot without requiring an unusually strong primordial fluctuation. Testing these alternative theories requires distinguishing their predictions from those of the standard model. For bubble collisions, that means looking for specific geometric signatures. For modified gravity, it means measuring how the integrated Sachs-Wolf effect scales, with void size across many examples, not just the cold spot. For inhomogeneous dark energy, it means mapping the expansion rate of the universe in different directions to check for spatial variations. These tests are challenging, but upcoming surveys and experiments may provide the necessary data. Despite the appeal of exotic explanations, most cosmologists remain skeptical. The cold spot, while unusual, isn't so extreme that it demands abandoning the standard model. Science operates on the principle of parsimony. Prefer simpler explanations unless the data forces you to accept more complex ones. A rare statistical fluctuation combined with a large supervoid remains the simplest explanation consistent with the data, and until observations conclusively rule it out, more speculative ideas remain just that: speculation, other voids and large-scale structures. The Eridanus supervoid, if confirmed at its reported size, would rank among the largest known structures in the universe. But it's not alone. Over the past few decades, astronomers have discovered numerous other giant voids and vast structures that challenge our understanding of cosmic architecture. Comparing the Eridanus feature to these other discoveries helps place it in context and sheds light on whether it represents a genuine anomaly or simply the large end of a continuous distribution. One of the earliest giant voids discovered was the Boötes void, identified in 1981 by Robert Kirshner and colleagues. Spanning roughly 330 million light-years across, the Boötes void contains only about 60 galaxies where thousands would normally be expected. It's sometimes called the Great Void and remains one of the most prominent examples of underdense regions in the local universe. Subsequent surveys found additional large voids: the Sculptor void, the Capricornus supervoid, and others, each spanning hundreds of millions of light-years. Galaxy surveys conducted over the past 2 decades have revealed that voids are common features of the cosmic web. They're not anomalies but integral parts of large-scale structure, occupying perhaps 80% of the universe's volume. Most matter resides in the filaments and clusters that border voids, leaving the interiors relatively empty. Voids come in a range of sizes, from small cavities tens of millions of light-years across to giant voids several hundred million light-years in diameter. The size distribution follows a predictable pattern determined by the initial spectrum of density fluctuations and the subsequent gravitational evolution. But the Eridanus supervoid, at 1.8 billion light-years across, if that measurement holds, sits at the extreme tail of this distribution. Only a handful of structures approach or exceed that size. One is the giant void, located about 1.5 billion light-years away in the direction of the constellation Canes Venatici. Another is the so-called local hole, or KBC void, a large underdense region centered relatively close to the Milky Way, which some studies suggest could extend up to 1 billion light-years across. These structures push the limits of what standard cosmology predicts should exist, but they're not necessarily impossible. Complicating matters, defining a void's size is subjective. Should it be measured by the region's radius, its volume, or the total deficit of galaxies? Different definitions yield different rankings. Some voids are nearly spherical, others are elongated or irregular. Some have sharp boundaries, others fade gradually into denser surroundings. The Eridanus supervoid in particular appears to have a complex filamentary shape rather than being a simple sphere, making direct size comparisons tricky. On the opposite end of the density spectrum, astronomers have also identified enormous concentrations of matter walls, filaments, and superclusters stretching across hundreds of millions or even billions of light-years. The Sloan Great Wall, discovered in 2003, is a massive chain of galaxy clusters and filaments stretching 1.4 billion light-years. The Hercules Corona Borealis Great Wall, identified in 2013, spans an astonishing 10 billion light-years, making it the largest known structure in the observable universe. These walls form where multiple filaments of the cosmic web intersect, creating regions of exceptionally high galaxy density. The existence of such large structures raises the same questions as giant voids. How did they form so quickly? The standard answer invokes the hierarchical nature of structure formation. Small fluctuations collapse first, forming galaxies. Galaxies merge into clusters. Clusters align along filaments. Filaments connect into walls. At each stage, gravity amplifies the structure, and over billions of years, the cosmic web emerges. Simulations show that this process can produce walls and voids approaching the sizes observed, though the largest examples are rare, expected to appear only in a tiny fraction of the universe's volume. The key insight is that these structures aren't necessarily coherent in a physical sense. The Sloan Great Wall isn't a single bound object. It's a statistical alignment of smaller structures that happen to lie along a common plane. Similarly, the Eridanus supervoid might be a statistical alignment of smaller voids, rather than one unified structure. If so, the tension with cosmological models eases considerably, since each component is well within the expected size range. However, not everyone agrees with this interpretation. Some researchers argue that these large-scale patterns reflect real physical correlations in the initial density field seeded during inflation that persist across vast distances. If true, the presence of structures like the Eridanus Supervoid and the Hercules Corona Borealis Great Wall might indicate that the primordial fluctuation spectrum has more power on large scales than standard inflation models predict. This would represent a subtle but important deviation from the simplest inflationary scenarios. Another consideration is the role of cosmic expansion and dark energy. As the universe expands and dark energy begins to dominate, the growth of structure slows and eventually stops. Voids, in particular, are sensitive to dark energy because they're expanding regions. In a universe with dark energy, voids grow faster than they would in a matter-only universe, potentially creating larger underdense regions than earlier models predicted. Some studies suggest that the Eridanus supervoid size, while large, is consistent with what's expected in a lambda CDM universe with dark energy, provided we account for the randomness inherent in structure formation. Comparing the cold spots-associated supervoid to other known voids also reveals interesting patterns. Most large voids aren't associated with corresponding cold spots in the cosmic microwave background. This is partly because not all voids lie at the right distance to produce a strong integrated Sachs-Wolf effect. Voids need to be at intermediate redshifts, roughly 1 to 3 billion light-years away, to contribute significantly. Voids closer to us or farther away produce weaker signals. The Eridanus supervoid sits in the sweet spot, which is why it allegedly produces a detectable temperature deficit. Statistical studies have searched for correlations between voids and cold spots across the entire sky. The results show a general trend. Directions toward large voids do tend to be slightly colder in the cosmic microwave background, consistent with the integrated Sachs-Wolf effect. But the cold spot remains an outlier colder than what the average void of its size should produce. This brings us back to the central mystery. Is the cold spot simply an unusually strong combination of a large void and a primordial fluctuation, or does it indicate something more profound? The axis of evil and other cosmic microwave background anomalies. The cold spot isn't the only puzzling feature in the cosmic microwave background. Over the past 2 decades, astronomers have identified several other anomalies patterns in the microwave sky that don't quite match the predictions of standard cosmology. While each anomaly could potentially be explained as a statistical fluke, taken together they've prompted some researchers to wonder whether the lambda CDM model is missing something important. The most famous of these is the so-called axis of evil. The axis of evil refers to an unexpected alignment in the largest scale temperature fluctuations in the cosmic microwave background. When astronomers decompose the microwave sky into spherical harmonics, mathematical functions describing patterns at different angular scales, they find that the lowest order harmonics, corresponding to the largest structures, don't point in random directions as expected. Instead, they align along a common axis, roughly perpendicular to the plane of the solar system. This alignment appears to violate the cosmological principle, the assumption that the universe has no preferred directions and looks roughly the same from any vantage point. The term axis of evil was coined somewhat tongue-in-cheek by cosmologist João Magajo, but the anomaly is taken seriously. If real, it suggests that either the universe isn't as isotropic as we thought, or there's some systematic error in how we're measuring or interpreting the data. Early speculation blamed foreground contamination, microwave radiation from the Milky Way, or the solar system, interfering with the cosmic signal. But even after extensive efforts to remove such contamination, the alignment persists in both WMAP and Planck data. Another anomaly involves the so-called quadrupole and octupole moments, the second and third lowest spherical harmonic modes. These modes measure temperature fluctuations on the very largest angular scales, corresponding to structures spanning a significant fraction of the observable universe. According to standard inflation models, these modes should have roughly similar amplitudes to modes at slightly smaller scales, but observations show they're unexpectedly lower in amplitude than models predict. This low quadrupole problem has been debated since COBE first measured the cosmic microwave background in the early 1990s. Some researchers argue it's a statistical fluke. With only a few modes at these larger scales, it's not surprising that a couple might deviate from expectations. Others suggest it could indicate the universe is smaller than we think, with a non-trivial topology that suppresses the largest fluctuations. Still others propose it reflects physics beyond the standard model, perhaps related to the pre-inflationary state or boundary conditions during inflation. A related anomaly is the hemispherical asymmetry. When astronomers compare the two halves of the sky divided along a particular axis, they find that one hemisphere shows slightly stronger temperature fluctuations than the other. The difference is small, only a few percent, but statistically significant. This asymmetry wasn't predicted by any standard model, and suggests either a preferred direction in the universe or some subtle systematic effect not yet accounted for in the data analysis. The cold spot fits into this broader pattern of anomalies. Like the axis of evil and the hemispherical asymmetry, it represents a large-scale feature that seems improbable under standard assumptions. Some researchers have suggested that all these anomalies might share a common origin, perhaps a feature of inflation that generates correlations between widely separated regions, or a subtle violation of statistical isotropy encoded in the initial conditions of the universe. One proposed explanation invokes a phenomenon called superhorizon fluctuations. During inflation, quantum fluctuations are stretched beyond the size of the observable universe. We can't see these ultra-large-scale modes directly because they extend beyond our cosmic horizon, but they would produce a slight tilt or gradient across the visible universe. If such a gradient exists, it could manifest as anomalies like the hemispherical asymmetry or the axis of evil. The cold spot might represent a localized region where this superhorizon mode happens to align with other fluctuations, creating an unusually strong feature. Another idea suggests the anomalies arise from non-Gaussianity in the primordial fluctuations. Standard inflation predicts that temperature fluctuations should follow a Gaussian distribution, a bell curve, with no skewness or preferred correlations. But more complex inflation models allow for slight deviations from Gaussianity, which could enhance the probability of rare, large-scale features. If the universe's initial fluctuations were even slightly non-Gaussian, it might explain why we see more anomalies than expected. Testing these ideas requires precise measurements and careful statistical analysis. Planck's final data release in 2018 included extensive searches for non-Gaussianity, testing dozens of different models and scenarios. The results were largely consistent with Gaussian fluctuations, but some hints of non-Gaussianity remained, particularly on large angular scales. Whether these hints represent real physics or statistical noise remains uncertain. Critics of the anomaly hunting argue that astronomers are falling into a statistical trap known as the look elsewhere effect. If you search a dataset for unusual features without specifying in advance what you're looking for, you're almost guaranteed to find something. The human brain is adept at recognizing patterns, even in random data, and the cosmic microwave background contains millions of resolution elements. With so many potential features to examine, finding a few that appear anomalous is inevitable. Proponents counter that the anomalies aren't arbitrary, they involve specific, physically meaningful scales and patterns. The axis of evil, for instance, aligns with the solar system, which is suspicious and might suggest foreground contamination, but it's also aligned with the quadrupole and octopole modes, which is harder to explain as coincidence. The cold spot is unusual not just because it's cold, but because it's both cold and large and sits in a region with a known supervoid. These aren't random features, they're structured in ways that demand explanation. The debate remains unresolved. Future cosmic microwave background experiments will provide more precise data, potentially confirming or refuting these anomalies. Meanwhile, theorists continue to explore whether slight modifications to inflation, such as multiple inflaton fields, features in the inflaton potential, or deviations from slow roll dynamics could produce the observed patterns without requiring entirely new physics. Testing cosmological principles. The existence of the Eridanus supervoid and other large-scale structures raises fundamental questions about the cosmological principle, the assumption that the universe is homogeneous and isotropic on sufficiently large scales. This principle underpins all of modern cosmology. It states that if you zoom out far enough, the universe looks roughly the same everywhere and in all directions. There are no special locations, no preferred directions, and no structures so large they dominate the cosmic landscape. The cosmological principle allows astronomers to apply Einstein's field equations to the universe as a whole, treating it as a smooth, uniform fluid rather than a chaotic jumble of galaxies and voids. This simplification makes cosmology tractable. Without it, every region of space would require its own set of equations, and predicting the universe's evolution would become impossibly complex. But how large is sufficiently large? At what scale does the universe transition from lumpy to smooth? Galaxy surveys show that on scales of tens of millions of light-years, the universe is highly inhomogeneous, full of clusters, filaments, and voids. But as you average over larger and larger volumes, the fluctuations smooth out. By scales of several 100 million light-years, the universe's density becomes nearly uniform, with variations of only a few percent. This transition scale, sometimes called the homogeneity scale, is predicted by the lambda CDM model to be around 300 to 500 million light-years. The problem is that structures like the Eridanus Supervoid, the Sloan Great Wall, and especially the Hercules Corona Borealis Great Wall exceed this scale, some by a significant margin. If these structures are truly coherent, they challenge the notion that the universe becomes smooth above the homogeneity scale. They suggest that large-scale inhomogeneities persist to sizes larger than the model predicts, potentially violating the cosmological principle. Defenders of the standard model argue that these structures aren't truly coherent. The Sloan Great Wall, for example, is a statistical overdensity, a region where galaxies happen to align along a common axis, but it's not a single-bound object. Its components aren't gravitationally connected, and they're not evolving as a unified system. Similarly, the Eridanus Supervoid might be a chance alignment of smaller voids rather than one unified structure. If so, the cosmological principle remains intact, because the universe does smooth out on large scales when you account for random alignments. But proving whether these structures are coherent or coincidental requires detailed observations and simulations. Some studies have used computer simulations to ask, how often do structures as large as the Eridanus Supervoid or the Hercules Corona Borealis Great Wall appear in model universes generated from standard cosmology? The answer depends on how you define structure and what volume of space you survey. In simulations covering a region the size of the observable universe, such features do appear occasionally, but they're rare, found in only a small fraction of simulated universes. This rarity doesn't necessarily mean the structures violate the cosmological principle. Rare events happen. The question is whether they happen rarely enough to remain consistent with standard models, or so rarely that we need to rethink our assumptions. Statistical tests comparing the observed distribution of large-scale structures to simulations suggest the two are broadly compatible, though with some tension. The real universe appears slightly lumpier on large scales than simulations predict, but not drastically so. Another way to test the cosmological principle is to measure how cosmic expansion varies across the sky. If the universe is truly isotropic, the Hubble constant, the rate at which space expands, should be the same in every direction. Astronomers have conducted this test by measuring the redshifts and distances of galaxies distributed across the sky. The results show that, within current measurement uncertainties, the expansion rate is indeed isotropic. There's no evidence for a preferred direction or a cosmic axis along which expansion proceeds differently. However, some researchers have claimed tentative evidence for anisotropic expansion at low statistical significance. If confirmed by future observations, this would represent a profound violation of the cosmological principle and would require rethinking the foundations of modern cosmology. For now, though, the evidence remains weak and disputed. A related test involves the cosmic microwave background's dipole, the temperature difference between opposite sides of the sky caused by Earth's motion through space. As our solar system moves relative to the cosmic rest frame, photons from the direction we're moving toward are blue-shifted, slightly warmer, while photons from behind are red-shifted, slightly cooler. This produces a dipole pattern with an amplitude of about 3.4 millikelvin, much larger than the primordial fluctuations, but easily accounted for by our motion. If the cosmological principle holds, the dipole we observe in the cosmic microwave background should match the dipole inferred from the distribution of galaxies. Both measure our motion through space, and they should agree. Studies comparing the two find good agreement, with only minor discrepancies that might be explained by local structures like the Virgo cluster pulling us off course. This consistency supports the cosmological principle and suggests that, despite anomalies like the cold spot, the universe behaves as expected on the largest scales. Implications for the multiverse. Among the most speculative explanations for the cold spot is the idea that it represents evidence of the multiverse. the hypothesis that our observable universe is just one bubble in an infinite expanse of other universes, each with potentially different physical constants, particles, and forces. The multiverse remains one of the most controversial ideas in theoretical physics, praised by some as a natural consequence of inflation and dismissed by others as untestable metaphysics. But if the cold spot truly resulted from a collision between our universe and another bubble universe, it would provide the first direct observational evidence that the multiverse exists. The multiverse concept arises naturally from eternal inflation, a variant of cosmic inflation in which the inflaton field doesn't roll down smoothly everywhere at once. Instead, quantum fluctuations cause some regions to keep inflating while others stop. The regions that stop form bubble universes, pockets of space where inflation has ended, and normal physical processes like galaxy formation can begin. Meanwhile, the regions that keep inflating continue spawning new bubbles, creating an eternally inflating multiverse with an infinite number of pocket universes. Each bubble universe has its own properties, determined by how the inflaton field and other fields settle into their ground states when inflation ends. In some bubbles, the electron might be heavier. In others, the strength of gravity might differ. In still others, the number of spatial dimensions might be different. Our universe, with its particular set of physical constants, is just one possibility among countless others. If two bubble universes happen to nucleate near each other during eternal inflation, they can collide. The collision would occur when the expanding walls of the bubbles touch, sending shock waves through both. In our bubble, such a collision would imprint a distinctive signature on the cosmic microwave background, a roughly circular region with a temperature profile depending on the collision's energy, angle, and timing. The signature would look like a disk in the sky, possibly with a cold center and a warmer ring around the edges, or vice versa. This prediction, first calculated in detail around 2007 by researchers including Matthew Kleben, Thomas Levi, and Chris Sigurdsson, generated excitement because it made the multiverse testable. If observers could find a disk-shaped temperature anomaly in the cosmic microwave background matching the predicted profile, it would constitute evidence for eternal inflation and the existence of other universes. When the cold spot appeared in WMAP data, some physicists wondered whether it might be exactly that, a cosmic bruise left by an ancient collision. Detailed analysis, however, failed to confirm this interpretation. Bubble collision signatures should have specific geometric properties, perfect or near-perfect circular symmetry, a temperature profile that rises or falls smoothly from the center to the edges, and possibly secondary rings caused by interference patterns. The cold spot, while roughly circular, isn't perfectly symmetric. Its temperature profile shows irregular fluctuations inconsistent with simple collision models. And its size, while large, doesn't match the expected angular scale for collisions that occurred during the inflationary epoch. Moreover, simulations of bubble collisions show that their signatures depend sensitively on the collision's parameters, the relative velocities of the bubbles, the energy difference between their vacuum states, and the angle of impact. Some collisions produce hot spots rather than cold spots. Others produce features so faint they'd be undetectable. The parameter space is vast, and finding a set of values that reproduces the cold spot's exact properties proved difficult. By 2010, most researchers concluded that the cold spot probably wasn't a bubble collision, but the search didn't end there. Astronomers began systematically scanning the entire cosmic microwave background for disk-shaped anomalies, searching for other potential collision signatures. Several studies examined Planck data, testing billions of circular regions across the sky for temperature profiles consistent with bubble collisions. They found several candidates regions that showed some of the expected features but none conclusive. Follow-up analysis revealed that most candidates could be explained by foreground contamination, instrumental noise, or random fluctuations in the primordial temperature field. The lack of clear bubble collision signatures doesn't disprove the multiverse. It's possible that collisions are rare, occurring in only a tiny fraction of bubble universes. It's also possible that our bubble formed early in the eternal inflation process and has since expanded so much that any collision signatures have been stretched beyond the observable universe's edge. Or perhaps the energy scales involved in bubble nucleation are such that collision signatures are too faint to detect with current instruments. Some theorists argue that the multiverse hypothesis is fundamentally unfalsifiable and therefore unscientific. If every possible observation can be explained by appealing to a different bubble with different properties, the theory makes no definite predictions and can't be tested. This criticism has sparked intense philosophical debates about the nature of scientific theories and the limits of empirical testability. Proponents counter that the multiverse is a prediction of well-established theories, specifically eternal inflation and string theory, both of which have other testable consequences. They argue that rejecting the multiverse because it's hard to test is premature. Science has confronted seemingly untestable ideas before black holes, for instance, and eventually found ways to observe them. Perhaps the same will happen with the multiverse. Regardless of one's philosophical stance, the cold spot has played an important role in these debates. It forced physicists to think seriously about what multiverse signatures might look like and how to search for them. It spurred detailed calculations of bubble collision dynamics and stimulated efforts to scan the cosmic microwave background for unusual features. Even if the cold spot turns out to be a supervoid and a statistical fluke, it has driven progress in theoretical cosmology and expanded the range of phenomena scientists consider observable. The role of dark energy. Dark energy, the mysterious force causing the universe's expansion to accelerate, plays a crucial but often underappreciated role in the cold spot story. Without dark energy, the integrated Sachs-Wolf effect wouldn't produce significant temperature signals from voids, and the cold spot's connection to the Eridanus supervoid would be far weaker. Understanding how dark energy influences cosmic structure and the cosmic microwave background is essential to interpreting the cold spot and similar anomalies. Dark energy was discovered in 1998 through observations of distant Type Ia supernovae. These exploding stars, which all have nearly identical peak brightnesses, serve as standard candles for measuring cosmic distances. When astronomers measured the distances to dozens of distant supernovae and compared them to the redshifts of their host galaxies, they found something unexpected. The universe's expansion wasn't slowing down as gravity pulled everything together. It was speeding up. This acceleration implies the existence of a repulsive force filling all of space dark energy. In the simplest models, dark energy is the cosmological constant, denoted by the Greek letter L, a term Einstein originally introduced to his field equations to create a static universe, then abandoned after Edwin Hubble discovered cosmic expansion. The cosmological constant represents vacuum energy, the intrinsic energy of empty space itself. Quantum field theory predicts that even empty space teems, with virtual particles popping in and out of existence, and this quantum activity contributes to the vacuum's energy density. Dark energy now dominates the universe's energy budget, comprising about 68% of the total. Its gravitational effect is repulsive rather than attractive, causing space to expand faster over time. This acceleration has profound consequences for the structure and evolution of the cosmos. In a universe dominated by matter alone, structures continue growing indefinitely as gravity pulls material into denser regions. But in a universe dominated by dark energy, structure growth slows and eventually stops because the accelerating expansion counteracts gravity's pull. Voids are particularly sensitive to dark energy. In a matter-dominated universe, voids expand slowly as galaxies on their edges move apart under the general cosmic expansion. But in an accelerating universe, voids expand faster. As they grow, their gravitational potential wells become shallower, less deep because they contain less and less matter relative to their volume. This changing potential well is what produces the integrated Sachs-Wolf effect. When photons from the cosmic microwave background pass through a void, they experience the void's gravitational potential at two different times, when they enter and when they exit. If the potential well is deeper when they enter than when they exit, because the void has expanded and become less dense, the photons lose net energy. They emerge cooler, producing a cold spot in the microwave background. The magnitude of this cooling depends on how much the void's potential changes during the light travel time, which in turn depends on the strength of dark energy and the rate of cosmic acceleration. The integrated Sachs-Wolf effect is one of the few direct probes of dark energy's properties. By measuring how much temperature shifts different voids produce, astronomers can test whether dark energy behaves like a cosmological constant or something more exotic. If dark energy's density remains constant over time, as the cosmological constant predicts, the integrated Sachs-Wolf effect should have a specific magnitude. If dark energy's density changes, either growing stronger or weaker, the effect's magnitude changes accordingly. Most observations to date are consistent with dark energy behaving like a cosmological constant, with an equation of state parameter wall, the ratio of pressure to energy density equal to -1. But uncertainties remain large, and hints of deviations appear in some datasets. The cold spot, if its temperature deficit exceeds what standard dark energy models predict, could be one such hint. If the Eridanus supervoid produces a stronger than expected cooling signal, it might suggest dark energy has unusual properties, perhaps varying in density across space or evolving over time in unexpected ways. Some alternative dark energy models have been proposed specifically to address anomalies like the cold spot. One idea is clustered dark energy, where dark energy's density is slightly higher in underdense regions like voids and lower in overdense regions like clusters. This spatial variation would enhance the integrated Sachs-Wolf effect, allowing smaller or less extreme voids to produce larger temperature signals. However, most clustered dark energy models face theoretical difficulties and lack independent observational support. Another speculative idea involves interacting dark energy, where dark energy exchanges energy with dark matter or ordinary matter. Such interactions could affect the growth rate of structure and the evolution of voids, potentially producing larger temperature signals. But like clustered dark energy, interacting models are highly constrained by observations of galaxy clustering, supernova distances, and the cosmic microwave background itself. Modified gravity theories offer yet another approach. Instead of adding a new dark energy component, these theories propose that Einstein's general relativity breaks down on cosmological scales. Modifications like FR gravity or scalar tensor theories change how gravitational potentials evolve over time, altering the integrated Sachs-Wolf effect. Some modified gravity models predict enhanced temperature signals from voids, potentially explaining the cold spot without invoking statistical flukes or exotic structures. Testing these ideas requires measuring the integrated Sachs-Wolf effect across many voids, not just the Eridanus supervoid. By stacking the signals from hundreds or thousands of voids identified in galaxy surveys and cross-correlating them with cosmic microwave background maps, astronomers can measure the average effect and compare it to predictions from different dark energy and modified gravity models. Such studies have been conducted using WMAP and Planck data, and the results generally favour standard dark energy, but with enough statistical uncertainty to leave room for alternatives. Future surveys like Euclid and Rubin will identify many more voids across a wider range of distances and sizes, allowing much more precise measurements of the integrated Sachs-Wolf effect. These measurements will test whether dark energy truly behaves like a cosmological constant or exhibits more complex behaviour. If the cold spot's association with the Eridanus supervoid is typical, then dark energy is behaving as expected. If it's anomalous, producing a much stronger signal than other voids, it could indicate new physics. The baryon acoustic oscillation connection. The Eridanus supervoid presents challenges that extend beyond temperature anomalies and statistical improbabilities. One particularly intriguing aspect involves its relationship to baryon acoustic oscillations, relics of sound waves that propagated through the primordial plasma before recombination. These oscillations left a characteristic imprint on the distribution of matter throughout the universe, creating a standard ruler that cosmologists use to measure cosmic distances and test the geometry of space-time. The question is whether the supervoid distorts or respects this fundamental cosmic pattern. Baryon acoustic oscillations originated in the first few 100,000 years after the Big Bang, when the universe was a hot, dense plasma of photons, electrons, and atomic nuclei. Pressure waves essentially sound rippled through this plasma, driven by the competing forces of gravitational attraction pulling matter inward and radiation pressure, pushing it outward. These waves propagated at roughly half the speed of light until recombination occurred and the universe became transparent. At that moment, the waves froze in place, leaving an imprint on the distribution of matter that persists today. This imprint appears as a subtle excess in the probability of finding pairs of galaxies separated by a specific distance, roughly 490 million light-years in today's universe, though the exact value depends on cosmic expansion history. When astronomers survey large volumes of space and measure the clustering of galaxies, this characteristic scale emerges as a small bump in the correlation function. It serves as a cosmic measuring stick, allowing researchers to determine distances across billions of light-years and trace how the universe has expanded over time. The Eridanus supervoid, spanning nearly 2 billion light-years, encompasses multiple baryon acoustic oscillation wavelengths. If the void formed through normal gravitational processes amplifying primordial density fluctuations, it should respect the baryon acoustic oscillation pattern. The distribution of galaxies within and around the void should still show the characteristic 490 million light-year spacing, just with an overall reduced density. But if the void represents something anomalous, perhaps a non-Gaussian fluctuation, or a feature imprinted during a non-standard inflationary epoch, the baryon acoustic oscillation signal might be distorted or suppressed. Measuring this requires extraordinarily precise galaxy surveys. Researchers must map not just whether galaxies are present or absent in a given region, but their exact three-dimensional positions and how they cluster relative to one another. Early analyses using photometric redshifts from surveys like WISE and PAN-STARRS lacked the precision needed to detect baryon acoustic oscillations within the supervoid. The uncertainties in galaxy distances, typically tens or hundreds of millions of light-years for photometric measurements, smeared out the signal, making it impossible to distinguish the characteristic scale from noise. Spectroscopic surveys offer better precision. By obtaining detailed spectra for thousands of galaxies within the Eridanus region, astronomers can measure their redshifts to accuracies of a few million light-years or better. The Sloan Digital Sky Survey's BOSS and eBOSS programs, designed specifically to measure baryon acoustic oscillations across large cosmic volumes, included some coverage of the Eridanus region. Preliminary analyses suggested the baryon acoustic oscillation signal within the supervoid appeared weaker than in typical regions, but the statistical significance remained marginal. This potential suppression, if confirmed, would be significant. Baryon acoustic oscillations are remarkably robust. Simulations show they survive even in highly overdense or underdense regions, maintaining their characteristic scale despite local density variations. Observing a reduced signal within the supervoid might indicate something unusual about its formation history or internal dynamics. Perhaps the void formed earlier than typical voids, during an epoch when baryon acoustic oscillations hadn't fully established themselves. Or perhaps the void's extreme underdensity disrupts the clustering patterns in ways not captured by standard simulations. Another possibility involves selection effects. Voids contain fewer galaxies, and spectroscopic surveys often target brighter galaxies that are easier to observe. If the brightest galaxies in voids have different clustering properties than fainter ones, the measured baryon acoustic oscillation signal could appear distorted even if the underlying matter distribution follows the expected pattern. Distinguishing genuine physical effects from observational biases requires careful analysis and large sample sizes. Euclid will transform this field. With spectroscopic measurements for millions of galaxies across the Eridanus region, it will measure baryon acoustic oscillations within the supervoid with unprecedented precision. If the signal matches expectations, it will confirm that the void formed through standard gravitational processes, and that its size, while unusual, doesn't violate fundamental cosmological principles. If the signal appears anomalous, either suppressed or shifted to different scales, it would strengthen the case that something about the supervoid's origin or evolution lies outside current models. Baryon acoustic oscillations also provide a test of modified gravity theories. In general relativity, the oscillation's characteristic scale depends only on the sound speed in the primordial plasma and the distance sound waves travelled before recombination. But in modified gravity theories, where the strength of gravity changes with scale or evolves over time, the effective sound speed and the subsequent gravitational amplification of density fluctuations could differ subtly from standard predictions. Measuring baryon acoustic oscillations in extreme environments, like the Eridanus supervoid probes, gravity in regimes where deviations might be most apparent. The interplay between baryon acoustic oscillations and the integrated Sachs-Wolf effect offers another diagnostic. Both phenomena depend on how matter is distributed across large scales, but they probe different aspects of cosmic evolution. Baryon acoustic oscillations trace the initial conditions set during recombination, while the integrated Sachs-Wolf effect measures how gravitational potentials evolve as photons traverse voids. By comparing the two signals within the same region, astronomers can test whether the supervoid's properties, its depth, size, and density profile are internally consistent, or whether different measurements yield conflicting pictures. The next generation of surveys will settle these questions. Until then, the the baryon acoustic oscillation connection to the Eridanus supervoid remains an intriguing piece of the puzzle, hinting that the void's influence extends beyond temperature anomalies to potentially affect one of cosmology's most fundamental standard rulers, the supervoid's gravitational lensing signature. While much attention is focused on the Eridanus supervoid's effect on the cosmic microwave background, another observable signature offers a complementary probe: gravitational lensing. As light from distant galaxies passes through the void, the reduced gravitational field along the line of sight should produce measurable distortions in the shapes and positions of background sources. This weak lensing signal, though subtle, provides an independent method to map the void's mass distribution and test whether its properties match predictions from its inferred galaxy deficit. Gravitational lensing occurs because mass warps spacetime, bending the paths of light rays passing nearby. In regions with high mass density galaxy clusters, for example, the lensing is strong, producing dramatic effects like multiple images of background galaxies, giant arcs, and highly magnified sources. In underdense regions like voids, the effect is inverted. The absence of mass means less gravitational bending, causing light rays to converge slightly less than they would in an average region. Background galaxies appear subtly less distorted, slightly larger, and fractionally brighter than if the void weren't there. Detecting this signal requires measuring the shapes of millions of galaxies with exquisite precision. Gravitational lensing distorts galaxy images by only a few %, and each individual galaxy has an intrinsic shape unrelated to lensing. The challenge is to average over thousands or millions of galaxies, measuring their collective distortion pattern and separating the lensing signal from intrinsic shape noise. This technique, called weak gravitational lensing, has become one of cosmology's most powerful tools over the past 2 decades. For the Eridanus supervoid, weak lensing offers several advantages over galaxy redshift surveys. It measures the total mass along the line of sight, including any dark matter that doesn't emit light, rather than just counting visible galaxies. If the void contains unexpected amounts of dark matter, perhaps in the form of primordial black holes or some other exotic component, weak lensing would detect it while galaxy surveys would miss it. Additionally, weak lensing isn't affected by the same selection biases that plague galaxy surveys, where faint objects go undetected and photometric redshifts introduce uncertainties. Early attempts to detect the supervoid's lensing signature, using the Canada-France-Hawaii Telescope Legacy Survey and other ground-based datasets, yielded ambiguous results. The surveys covered the Eridanus region but lacked sufficient depth and area to measure the weak lensing signal with high confidence. Analyses suggested a deficit in lensing convergence, the technical term for the cumulative lensing effect along a line of sight consistent with the presence of a large underdense region. But the statistical errors remained large. The signal was present at roughly 2 standard deviations, notable but not conclusive. Space-based observations offer better prospects. The Hubble Space Telescope's Cosmic Evolution Survey and other programs have mapped small patches of sky with extraordinary resolution, measuring galaxy shapes with minimal distortion from Earth's atmosphere. However, Hubble's field of view is tiny, and systematically surveying a region as large as the Eridanus supervoid would require impractical amounts of telescope time. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will combine Hubble-quality imaging with a field of view 100 times larger, making it ideal for weak lensing studies of large-scale structures. Euclid's weak lensing survey will provide the definitive measurement. By observing billions of galaxies across more than a third of the sky, Euclid will map the gravitational lensing signal at every location with high precision. For the Eridanus supervoid, this means measuring not just whether lensing is weaker on average, but how the lensing strength varies across the void's extent. Does the void have a sharp boundary where the lensing signal drops suddenly, or does it fade gradually into denser surroundings? Is the void roughly spherical, or does it have an elongated filamentary structure? These details reveal how the void formed and evolved. Comparing the weak lensing signal to the galaxy distribution provides a crucial consistency check. If both measurements indicate the same underdensity profile, the same depth, size, and shape, it confirms that visible galaxies accurately trace the underlying mass distribution. But if the lensing signal suggests more or less mass than the galaxy counts predict, it would indicate a disconnect between light and matter, potentially pointing toward unusual dark matter properties or systematic errors in one of the measurement techniques. One intriguing possibility is that the supervoid's lensing signature could reveal substructure, smaller voids, or filaments embedded within the larger, underdense region. Weak lensing maps have sufficient resolution to detect features tens or hundreds of millions of light-years across, allowing astronomers to peer inside the supervoid and examine its internal architecture. If the void consists of multiple smaller voids aligned along the line of sight, as some galaxy surveys suggest, weak lensing should reveal this stacking pattern as a series of distinct, underdense regions separated by denser bridges. The integrated Sachs-Wolf effect and weak lensing probe the same gravitational potentials but at different times. The integrated Sachs-Wolf effect measures how potentials evolve as cosmic microwave background photons traverse the void over billions of years. Weak lensing measures the potential's instantaneous depth, how much mass is present along the line of sight right now. By comparing the two, astronomers can test whether gravitational potentials are evolving at the rate predicted by general relativity and the lambda CDM model. Discrepancies would suggest either modified gravity or unexpected dark energy dynamics. Future surveys will also measure gravitational time delays, the differential arrival times of light, from variable sources like quasars passing through voids versus denser regions. Though technically challenging, these measurements offer yet another probe of the gravitational potential, independent of both galaxy counts and shape distortions. Combined with baryon acoustic oscillations, the integrated Sachs-Wolf effect, and direct galaxy surveys, gravitational lensing contributes to a multifaceted observational campaign aimed at understanding whether the Eridanus supervoid is an extreme example of normal cosmic structure or something fundamentally different. The void's effect on cosmic time. Time itself bends in the presence of mass, and the Eridanus supervoid, with its profound absence of matter, creates a subtle but measurable distortion in how cosmic time flows. This phenomenon, predicted by general relativity but rarely discussed in the context of large-scale structure, offers yet another window into understanding whether the supervoid represents ordinary cosmic evolution or something more fundamental. Einstein's theory tells us that clocks run slower in strong gravitational fields. Near a black hole, time dilates dramatically. Near Earth, the effect is tiny but measurable by atomic clocks. Extend this principle to cosmological scales, and an intriguing prediction emerges. Time should flow slightly faster in underdense regions like voids compared to dense regions like galaxy clusters. The difference is minuscule, perhaps a few parts per billion over cosmic timescales, but modern precision cosmology operates at exactly these levels of sensitivity. For the Eridanus supervoid, this time dilation effect manifests in several observable ways. First, the redshifts of galaxies within the void contain a gravitational component beyond the usual Doppler shift from cosmic expansion. Photons climbing out of the void's shallow gravitational well lose less energy than photons escaping denser regions, creating a slight blue shift relative to expectations. This gravitational redshift difference, though dwarfed by expansion-driven redshift, becomes statistically detectable when averaged over thousands of void galaxies. Measuring this requires comparing the observed redshifts of galaxies inside the supervoid to predictions based on their distances derived independently through standard candles like Type Ia supernovae or Cepheid variables. The handful of supernovae observed in the Eridanus region so far show redshifts broadly consistent with expectations, but the sample size remains too small for definitive conclusions. Future transient surveys will discover hundreds of supernovae across the supervoid's extent, enabling precise tests of whether gravitational time dilation matches general relativity's predictions in this extreme environment. The time dilation effect also influences the ages of stellar populations. Stars and galaxies within the void experience slightly faster cosmic time than stars in denser regions at the same cosmic epoch. This means stellar evolution proceeds marginally faster, old stars appear slightly more evolved, and galaxies should show subtly different star formation histories. The effect is small, perhaps a few million years over billions, but detectable with detailed spectroscopic studies of galaxy populations. Astronomers can test this by comparing the ages of globular clusters and elliptical galaxies in the supervoid to similar systems outside it. Globular clusters serve as excellent cosmic chronometers because their ages can be determined precisely by modelling the temperatures and luminosities of their oldest stars. If clusters within the void appear systematically older than those at similar redshifts in denser regions, after accounting for differences in formation history and metallicity, it would confirm the time dilation effect and provide an independent measurement of the void's gravitational potential depth. The cosmic microwave background's passage through the void also encodes time dilation information. As photons traverse the underdense region, they experience not just the integrated Sachs-Wolf effect, the energy change from evolving gravitational potentials, but also a relativistic Doppler shift from the void's peculiar velocity relative to the cosmic rest frame. Voids typically expand faster than average cosmic expansion, creating bulk flows that impart additional redshift or blue shift to transiting photons. Disentangling this kinematic effect from the gravitational time dilation requires detailed modelling of the void's velocity field, mapped through galaxy redshift surveys. Modified gravity theories make different predictions for time dilation in voids compared to general relativity. In FR gravity and scalar tensor theories, the effective gravitational potential depends not just on mass density, but also on additional scalar fields or curvature-dependent terms. These modifications can strengthen or weaken time dilation effects in underdense regions, offering another test to distinguish Einstein's theory from alternatives. If time dilation measurements in the Eridanus supervoid deviate from general relativity's predictions while lensing and baryon acoustic oscillations remain consistent, it would pinpoint modifications to gravity's time evolution component specifically. The relationship between time dilation and the integrated Sachs-Wolf effect reveals deeper connections. Both phenomena arise from gravitational potentials, but they probe different aspects. Time dilation measures the potential's instantaneous depth, while the integrated Sachs-Wolf effect measures how it changes over time. In standard cosmology with a cosmological constant, these two quantities are related through specific equations governing structure growth and dark energy's influence. Measuring both independently provides a consistency check on lambda CDM and constrains the properties of dark energy. Future gravitational wave detectors might eventually contribute insights. If binary black holes or neutron stars merge within the supervoid, their gravitational wave signals would carry imprints of the local gravitational potential and time dilation. The observed chirp mass, the combination of binary component masses inferred from the gravitational wave frequency evolution, would differ slightly from the true masses due to the void's gravitational environment. While detecting such subtle effects lies beyond current capabilities, next-generation detectors like the Einstein telescope or Cosmic Explorer might achieve the necessary precision. The Eridanus supervoid's time dilation signature thus adds another layer to the observational puzzle. It connects the void's influence on cosmic microwave background photons, galaxy evolution, and the fundamental flow of cosmic time itself. Whether these connections reveal standard physics operating in an extreme environment or hint at departures from general relativity and lambda CDM remains an open question, one that the next generation of surveys and precision measurements will finally answer. What we've learned and what remains unknown. Nearly 2 decades after its discovery, the cold spot remains one of astronomy's most intriguing mysteries. It has spurred hundreds of research papers, prompted the development of new observational techniques, and forced cosmologists to confront the limits of the standard model. Yet despite all this effort, fundamental questions remain unanswered. Is the cold spot a rare statistical fluke, a supervoid-enhanced primordial fluctuation, or evidence of something beyond current cosmological theories? What we've learned is substantial. The cold spot is real, not an instrumental artifact or data processing error. Multiple independent satellites and ground-based telescopes have confirmed its existence. It does coincide with a large underdense region, the Eridanus supervoid, which extends across 1 to 2 billion light-years at a distance of roughly 3 billion light-years from Earth. This supervoid contributes to the cold spot's temperature deficit through the integrated Sachs-Wolf effect, accounting for perhaps 20 to 30% of the observed cooling. We've also learned that the cold spot isn't the only anomaly in the cosmic microwave background. The axis of evil, hemispherical asymmetry, and low quadrupole power all suggest that something unusual is happening on the largest observable scales. Whether these anomalies share a common origin or represent independent statistical flukes remains unclear, but their collective presence has convinced many cosmologists that the standard lambda CDM model, while remarkably successful, might not be the complete story. We've learned that large-scale structures like the Eridanus supervoid, while rare, aren't impossible within the standard model. Simulations show that voids approaching the supervoid's size do form occasionally, though finding one aligned with a strong primordial cold spot requires a degree of cosmic coincidence. The question isn't whether such structures can exist, but whether they exist at the frequency and magnitude we observe. What remains unknown is whether the cold spot requires new physics or simply represents the tail end of normal statistical variation. Calculating the exact probability of the cold spot's existence depends on numerous assumptions about how to define the feature, what statistical tests to apply, and how to account for selection effects. Different methods yield probabilities ranging from roughly 1 in 50 to 1 in several thousand. Is that rare enough to demand exotic explanations? There's no objective threshold. Science involves judgment calls about when to accept unlikely events as chance and when to seek deeper explanations. We don't know for certain whether the Eridanus supervoid is one structure or multiple aligned voids. Current galaxy surveys lack the resolution and depth to definitively resolve its three-dimensional structure. Euclid's upcoming data should clarify this, but until then, uncertainty remains. If it's one unified structure, it's among the largest ever discovered. If there are several smaller voids, the tension with cosmological models eases considerably. We don't know whether dark energy behaves identically everywhere in the universe. The cold spot could be probing a region where dark energy's density differs slightly from the cosmic average, producing a stronger than expected integrated Sachs-Wolf effect. Most observations suggest dark energy is uniform, but small variations are allowed within current constraints. Testing this requires measuring the integrated Sachs-Wolf effect across many locations, comparing regions with voids to regions without, and checking for consistency. We don't know whether inflation operated exactly as the simplest models predict. The cold spot and other large-scale anomalies could be hinting at more complex inflationary dynamics, multiple inflation fields, features in the inflation potential, or deviations from slow-roll behavior. These possibilities are difficult to test because they involve physics at energy scales far beyond what particle accelerators can reach. The cosmic microwave background offers one of the few windows into inflation, but interpreting its signals requires disentangling primordial effects from later gravitational evolution. We don't know whether the cosmological principle, the assumption that the universe is statistically homogeneous and isotropic, holds perfectly on the largest scales. The cold spot, if confirmed as more extreme than standard models predict, could indicate preferred directions or inhomogeneities beyond the homogeneity scale. But proving this requires surveying vast volumes of space, comparing observations to simulations, and carefully accounting for selection effects and observational biases. Perhaps most fundamentally, we don't know whether the cold spot represents a window into new physics or a reminder of how probability works. Rare events, by definition, occasionally happen. In a universe large enough and old enough, improbable configurations will appear somewhere, sometime. The question is whether the cold spot is one such inevitability, or whether its existence signals something deeper, a clue that our cosmological models are missing an essential ingredient. The next decade promises answers. Euclid and Rubin will map the distribution of galaxies across billions of light-years with unprecedented precision. CMB, S4, and other microwave background experiments will measure temperature fluctuations down to the limits set by fundamental physics. Supercomputers will simulate ever larger and more realistic model universes, providing detailed predictions for comparison with observations. Machine learning algorithms will search the data for patterns too subtle for human analysts to spot. If future observations confirm that structures like the Eridanus supervoid are more common than current models predict, it would suggest the universe's large-scale structure is lumpier than expected, possibly indicating new physics in the early universe, or modifications to how gravity works on cosmic scales. If instead, the cold spot turns out to be a 1 in 1,000 statistical fluctuation rare, but consistent with lambda CDM, it will stand as a monument to the fact that the universe is large, complex, and full of surprises, even within the bounds of standard physics. Either outcome advances our understanding. Science progresses both by confirming theories and by finding their limits. The cold spot has already pushed cosmology forward, forcing researchers to think harder about large-scale structure, the limits of statistical reasoning, and the observable consequences of speculative ideas like the multiverse. Whether it ultimately proves to be a signpost to new physics or a cosmic curiosity, it has earned its place among astronomy's greatest puzzles, a billion light-year question mark written across the sky, waiting for the next generation of telescopes and minds to decode its meaning. Future observations and missions. Resolving the mysteries surrounding the Eridanus supervoid and the cold spot will require more data, deeper galaxy surveys, more sensitive cosmic microwave background measurements, and more sophisticated simulations. Several upcoming missions and observatories promise to deliver exactly that, potentially answering long-standing questions about the universe's largest structures and whether they represent genuine anomalies or rare but expected fluctuations. On the galaxy survey front, the European Space Agency's Euclid mission, launched in 2023, is designed to map the three-dimensional distribution of galaxies across more than a third of the sky out to distances exceeding 10 billion light-years. Euclid uses two instruments, a visible light camera and a near-infrared spectrometer, to measure galaxy positions, shapes, and redshifts with extraordinary precision. By mapping billions of galaxies, Euclid will construct the most detailed three-dimensional picture of the cosmic web ever created, revealing the distribution of voids, filaments, and clusters across cosmic time. Euclid's data will allow astronomers to measure the properties of voids, like the Eridanus supervoid, with unprecedented accuracy. Instead of relying on photometric redshifts with their inherent uncertainties, Euclid will provide spectroscopic redshifts for millions of galaxies, pinpointing their distances and allowing precise mapping of underdense regions. This will resolve lingering questions about whether the Eridanus feature is one giant void or multiple smaller ones, and whether its galaxy deficit is as extreme as early studies suggested. The Vera-Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, began operations in 2024 inches Chile. Its legacy survey of space and time will photograph the entire southern sky every few nights for 10 years, creating a time-lapse movie of the cosmos and cataloguing billions of galaxies, stars, and transient events. Rubin's photometric survey will complement Euclid's spectroscopic observations, providing wide-field coverage and detecting faint galaxies that might be missed by other surveys. Together, Euclid and Rubin will revolutionize our understanding of large-scale structure. They'll measure the distribution of matter across billions of light-years, testing whether the cosmic web matches the predictions of lambda CDM or reveals unexpected features. If structures as large as the Eridanus supervoid turn out to be more common than current data suggest, it would indicate that the standard model underestimates the clustering of matter on the largest scales, a potential sign of new physics. On the cosmic microwave background front, several ground-based experiments are pushing toward ever greater sensitivity. The Simons Observatory, located in the Atacama Desert of Chile, consists of multiple telescopes designed to measure the microwave background's temperature and polarization with exquisite precision. Its primary goals include detecting the faint swirl patterns in polarization caused by gravitational waves from inflation and measuring the properties of galaxy clusters through their distortion of the microwave background. But it will also provide new data on large-scale anomalies like the cold spot, potentially revealing subtle features invisible to earlier experiments. CMB S4, short for Stage 4 Cosmic Microwave Background, is a proposed next-generation experiment that would deploy dozens of telescopes across the South Pole and Chile, creating an observatory far more sensitive than any previous effort. CMB S4 would map the entire microwave sky with unprecedented resolution, measuring temperature fluctuations down to a few microkelvin and detecting millions of distant galaxy clusters through their gravitational effects on microwave photons. Such detailed maps could reveal whether the cold spot has substructure internal patterns that might distinguish between a primordial origin, a supervoid-induced effect, or something more exotic. Space-based missions are also in the planning stages. NASA and the European Space Agency have discussed concepts for a next-generation microwave background satellite that would surpass Planck's sensitivity and resolution, potentially detecting the faint polarization signal from gravitational waves predicted by inflation. Such a mission could also re-examine the cold spot and other anomalies with fresh instruments, confirming or refuting earlier findings and searching for new large-scale features. Advances in computational cosmology will also play a critical role. Modern supercomputers can simulate the evolution of the universe from the Big Bang to the present day, tracking billions of dark matter particles and gas elements as they collapse into galaxies, merge into clusters, and carve out voids. These simulations, with names like Illustris, EA-GEL, and Millennium, have become increasingly realistic, incorporating the effects of star formation, supernova feedback, black hole growth, and cosmic expansion. By running thousands of simulations with slightly different initial conditions, cosmologists can build a statistical library of model universes, each representing a possible realization of the lambda CDM model. Comparing the real universe to this library allows researchers to determine how unusual features like the Eridanus supervoid truly are. If similar structures appear in a few % of simulations, the cold spot is rare but expected. If they appear in less than 1%, the tension with standard models grows more serious. Simulations can also test specific scenarios. For example, researchers can simulate universes with slightly different amounts of dark energy, different inflation potentials, or modified gravity laws, then check whether these alternatives produce structures more consistent with observations. If one variant consistently matches the data better than standard lambda CDM, it might point toward new physics. Machine learning and artificial intelligence are also entering the fray. Algorithms trained on simulations can learn to recognize patterns in galaxy distributions, identifying voids, filaments, and clusters more accurately than traditional methods. These tools can process massive datasets from surveys like Euclid and Rubin, extracting features that human analysts might miss and testing cosmological models with greater efficiency. Another promising avenue involves improved measurements of the integrated Sachs-Wolf effect. By cross-correlating cosmic microwave background maps with three-dimensional galaxy surveys, astronomers can measure the statistical signature of voids and clusters on the microwave sky. This technique has already confirmed the integrated Sachs-Wolf effect as a real phenomenon, but future data will allow more precise measurements, potentially revealing whether the effect's strength matches predictions across a range of void sizes. If large voids like the Eridanus supervoid produce stronger than expected signals, it could indicate modifications to general relativity or unexpected properties of dark energy. Gravitational wave astronomy, though still in its infancy, might eventually contribute insights. If modifications to gravity or dark energy affect how spacetime vibrates, those effects could appear in the gravitational wave signals from merging black holes or neutron stars. While detecting such subtle effects lies far in the future, the rapid growth of gravitational wave observatories like LIGO, Virgo, and the future space-based LISA opens new windows on fundamental physics.